solids of revolution are certain solids that are formed by revolving an area around usually either the x-axis or the y-axis. All right, so let's just remember the fundamental theorem of calculus that states that, well, let's look at this limit, which sometimes represents the area or could represent the area under g of x from between 2 points A and B, that this area, which is a limit of rectangles, is equal to the antiderivative of g evaluated at B minus the antiderivative evaluated at A. So that's the fundamental theorem. Now, this limit could be interpreted as an area, but in some cases it has other interpretations. So this could be an area, or it could have another interpretation. Whatever makes sense in context, but the point is that it is equal to the antiderivative evaluated at the endpoints and subtracted. So just a little example of another interpretation. Let's say we're talking about a velocity function, and the antiderivative of velocity is distance. Let's let the letter s represent distance. So this is equal to s of b minus s of a. And the interpretation is, rather than area, the interpretation is distance traveled from time t equal a to time t equal b. Okay, so the point is this type of sum, which is where you have a function times delta x, is equal to the antiderivative at the second point minus the antiderivative at the first point. And we're going to use that to demonstrate the formulas that are appropriate for finding the volumes of solids of revolution. So let's look at the disk method, which is one method for finding the volume of a solid of revolution. So here we have a curve. Let's say this is y equal f of x. And we're looking at the area underneath y equal f of x between A and B, and we're going to rotate this about the x-axis, and that'll give us a solid, and we want to find the volume of that solid. So we break up this task. We start with the rotation of a little rectangle, a piece of the area, and we're just going to rotate that about the x-axis. Let's look at the dimensions of this rectangle. Well, the base of the rectangle is a little piece of the x-axis, so we'll call that dx. And the height, well, if this is point x over here, this height is f of x, so we'll call this height from here to here, that's f of x. Now we want to visualize the type of solid we would get if we just rotate this red rectangle about the x-axis. In this picture, we removed the red rectangle. We isolated it over here. You see it inside this disc. We spun it around the x-axis, so that's the resulting disc. It sort of looks like it's in the shape of a penny standing up on its side. And let's just take the volume of this disk. Well, notice that the height is the same as f of x right here. So the height is f of x. Well, actually not the height, but the radius. The radius of this disk is f of x. And the height, this is the height or the width or the thickness of the disk, that's dx, that comes from this. All right, so let's talk about the volume. Well, the volume, this disk is, the volume of this disk is going to be the base times the height. The base is this circle, pi r squared, and the height is h. All right, so let's call this volume, since it's only a piece of the volume that we want to calculate, let's call the volume delta V. Delta V meaning one slice of the volume. Okay, so we have delta V is equal to pi r squared, that's the area of the circle, times the thickness, dx. Or let's call it h. H for height. And now let's substitute in for r, we'll substitute f of x, and for h we'll substitute dx. Okay, so then we have pi f of x squared dx. So now the volume is gotten by summing up these slices. So we'll write it like this. The volume is the sum. Let's write I equals 0 to n minus 1 pi f of xi squared dx. And where is that xi exactly? Well, here, you see this x over here? We can actually think of that as x sub I. And if we have many of these along the interval between a and b, okay, those are the xi's that we're talking about. So we have this, the volume expressed, it's actually approximately equal to the sum of these disks. And now we take the limit as n goes to infinity, and this is equal to, and that's by the fundamental theorem, we get the integral of pi times f of x squared dx. So this is the basic formula for the method for the disk method. Okay, so that's the volume. And this is the disk method.